Section: Introduction. In this section, we have discussed how reinforcement learning from human feedback, RLHF, has been crucial in enhancing large language models, LLMs, by making them more capable and controllable. RLHF is widely used by top AI companies like OpenAI, Anthropic, Meta, and Google to align LLM models with human values. However, RLHF encounters various challenges such as biased data, unrealistic human decision-making models, and limited representation of human diversity. We believe that incorporating key concepts from social choice theory can help address many of the issues faced by RLHF. While LLMs trained solely on internet data may generate repetitive or harmful text, RLHF allows models to follow instructions and produce useful and safe outputs based on human judgments. RLHF involves collecting sample outputs from a pre-trained LLM, asking humans to choose the best ones based on specific criteria like helpful or unbiased, and using these preferences to refine the model for better outputs. From a social choice perspective, important questions arise. Who should evaluate the models? What criteria should they use? How should their evaluations be combined? And how do their expressed judgments reflect their actual preferences? Constitutional AI, CAI, offers an alternative approach through reinforcement learning from AI feedback, RLAIF, where humans create a constitution, outlining principles for guiding LLM training. However, determining who contributes to the constitution and how it is formulated remains a challenge. We argue that leveraging social choice tools and theories can help address these challenges in RLHF, guiding the design process towards socio-technical solutions. By applying social choice principles, we can determine which individuals should provide feedback, what type of feedback is valuable, and how to aggregate and utilize this feedback effectively. Approaching these issues systematically is likely to lead to a fairer system that considers input from a wider range of people, provides more accurate feedback, and garners broader support. While concerns about inconsistency in feedback from diverse groups exist, social choice theory offers insights to prevent irrational outcomes. Although computational social choice is well established, its connection to aligning modern AI systems remains underexplored. Further research is essential to address the intersection of value alignment, RLHF, and social choice effectively. Developing sound answers to these questions is crucial for building responsible AI systems that consider diverse stakeholder feedback. Ad hoc approaches may lead to systems that inadequately represent stakeholders, overlook critical issues, marginalize groups, and create conflicts among stakeholders or AI systems. Section Summary. In this section, we explore the role of reinforcement learning from human feedback, RLHF, in enhancing large language models, LLMs, and the challenges it faces, such as unrepresentative data and modeling human diversity. We argue that integrating core ideas from social choice theory can help address these challenges by determining whose preferences should influence decisions and how to aggregate them effectively. Additionally, we discuss constitutional AI, CAI, as an alternative approach that involves humans creating a constitution to guide LLM training, emphasizing the importance of applying social choice tools to ensure fair and ethical AI development. Section: Background. In this section, we need to understand some background information related to our research agenda. We are focusing on the concept of value alignment, which is crucial as AI systems become more advanced. Value alignment involves ensuring that AI systems act in ways that are in line with human and societal values. There are various approaches to value alignment, such as theoretical work on defining formal games for AI agents to align with humans, studying the relationship between neural network activations and morally relevant outputs, and evaluating the ethical behavior of current AI models. One popular approach to value alignment is reinforcement learning from human feedback, RLHF. RLHF involves several steps. Firstly, we collect preference data by generating and evaluating a dataset of model outputs. Humans are then asked to choose their preferred output from pairs of completions based on given prompts. The next step is to train a reward model that maps outputs to rewards. This model is optimized to match human preferences observed in the data. Finally, we use reinforcement learning to train a policy that maximizes rewards from the reward model. Due to the limitations of existing RL optimizers, new techniques have been proposed for optimizing models based on collected preference data. One such technique is direct preference optimization, DPO, which optimizes a model by directly working on the preference label dataset. Another technique, Kahneman-Tversky optimization, KTO, enables learning a policy from unpaired preferences. The effectiveness of these techniques depends on how well they align with human utility functions. Additionally, we explore constitutional AI, CAI, which involves using RL from AI feedback, RLAIF, techniques. By following a set of principles called a constitution, we use a separate language model to generate artificial preference and instruction data for model fine-tuning. The constitution consists of written principles that guide the critique phase, and the instruction data is curated by repeatedly sampling principles and asking the model to revise completions based on them. Feedback data is constructed by providing the feedback model with a prompt, a set of principles, and two completions labeled as answers from a previous RLHF dataset. The feedback model's output probabilities are recorded as training samples for the reward model. Section Summary. In this section, we delve into the background necessary for our proposed research agenda, which involves merging topics previously studied by separate communities. We focus on the importance of value alignment in advanced AI systems to ensure they adhere to human and societal values, exploring various approaches like RLHF and introducing novel techniques such as direct preference optimization, DPO, and Kahneman-Tversky optimization, KTO, to optimize model training based on preference datasets. Additionally, we introduce constitutional AI, CAI, that leverages RL from AI feedback, RLAIF, techniques, using a constitution of principles to generate artificial preference and instruction data for model fine-tuning. Section: Social Choice. In this section, we delve into the realm of social choice. Modern social choice theory took root in the 1950s with Arrow's impossibility theorem. Arrow tackled the challenge of merging the preferences of multiple individuals into a collective preference, considering various normative criteria. He established conditions such as the universal domain, which requires the aggregation function to be applicable to all individual preferences, and the independence of irrelevant alternatives, stating that the social preference between two options should only depend on individual preferences for those options. Arrow's groundbreaking theorem revealed that under certain conditions, the only feasible aggregation functions are dictatorship, where the preference of one individual dictates the collective choice. This concept extends to social choice functions, which aim to select a set of worthy alternatives or a single winner. Arrow's work sparked extensive research on relaxing his criteria to avoid undesirable outcomes like dictatorship. In the realm of AI alignment, we encounter collective decision problems, where we must determine the set of alternatives for evaluation. These alternatives could range from various AI systems to different responses generated by a language model. The challenge lies in defining a manageable set of alternatives for evaluation, considering the vast possibilities in AI systems. One approach is to view alternatives as probability distributions over responses, reflecting the stochastic nature of language models. This not only fosters creativity but also enhances fairness in responses. Social choice rules can be applied to probability distributions, allowing evaluators to express preferences between distributions or plain alternatives. Introducing a multi-winner rule offers a compromise between deterministic single-winner rules and probabilistic approaches. This rule selects a small number of winning answers that best represent the voter's preferences, providing a concise overview of potential answers. Through exploring different aggregation methods, we aim to address the challenges of aligning AI systems with human preferences effectively. Section Summary. In this section, we delve into the foundations of social choice theory, which originated in the 1950s with Arrow's impossibility theorem. Arrow's work focused on the challenge of aggregating individual preferences into a collective social preference while upholding key criteria like universal domain, independence of irrelevant alternatives, and Pareto efficiency. The theorem revealed that in systems with at least 3 alternatives, satisfying all these criteria without resorting to dictatorship is unattainable, leading to a vast exploration of alternative aggregation methods in social choice theory. Section: Who provides the human feedback? In this section, we consider who provides the human feedback for AI systems. We start by assuming there is a group of people, called the stakeholder population, who will be impacted by the AI system and whose opinions should be considered when aligning the system. However, it may not be practical to gather feedback from everyone in this population, so we need to select a smaller representative group to provide feedback. This selection process can be informed by social choice theory and statistical sampling methods. One approach is to choose representatives through methods like citizens' assemblies or voting procedures that aim to reflect the diversity of the stakeholder population. Alternatively, stakeholders could delegate their feedback rights to others, following a concept similar to liquid democracy. Previous studies have used platforms like Mechanical Turk, Upwork, Scale AI, or Lionbridge for evaluator recruitment in this context. Next, we explore the format of human feedback for AI systems. Human feedback can take various forms, drawing from preference elicitation techniques and communication complexity studies. The goal is to seek feedback that is natural for individuals to provide, informative about their preferences, and useful for aligning AI systems. Different formats of feedback can lead to different outcomes, so understanding the impact of these choices is crucial. We discuss multiple options for feedback formats, such as open-ended comments, sorting responses, or ranking neural networks. The choice of feedback format can influence the alignment of AI systems, especially if we do not fully grasp the behavioral implications of each format. There is a question of whether individuals should be allowed to choose the format in which they give feedback, which is not common in traditional social choice but could offer flexibility in expressing preferences. Overall, offering evaluators a range of feedback options on various aspects of the system's behavior and values can lead to a more comprehensive understanding of their preferences. This diverse feedback can then be transformed into a common data structure, like a utility function, to guide the alignment of AI systems effectively. Section Summary. In this section, we explore the importance of selecting a subset of the stakeholder population to provide feedback for AI systems, drawing on social choice theory and statistics for guidance. We also delve into the various formats of human feedback, emphasizing the need for natural, informative, and alignment-capable input types to effectively train AI systems. The discussion highlights the significance of understanding how different feedback formats can impact the alignment of AI systems and the potential for allowing individuals to choose their preferred feedback format. Section: Dealing with diverse and informal feedback. In this section, we will discuss how we can handle diverse and informal feedback in the context of reinforcement learning from human feedback, RLHF. In RLHF, human feedback is commonly used to train a reward model that assigns a numerical rating to AI system responses. This rating model can help convert varied feedback from different evaluators into a standardized form, which can then be combined with feedback from other evaluators to guide the AI system. To achieve this, we can train an evaluation interpretation model, denoted as phi, to map inputs like the prompt to the AI system, possible AI responses, evaluator features, evaluator feedback, and a specific response to a numerical evaluation. This model is typically based on a pre-trained language model that is fine-tuned for this specific task. The output of phi is a numerical rating given by an evaluator for a particular AI response, aiming to align with the evaluator's verbal feedback. We can view this task as a form of meta-learning. Using the trained evaluation interpretation model phi, we can then train another model called an individual preference model, denoted as psi. This model directly maps inputs like the prompt, possible AI responses, evaluator features, and a response to ratings. By using simulated ratings generated by Phi as training data, Psi aims to predict ratings for AI responses without relying on verbal evaluations. The hope is that the individual preference model Psi can predict ratings for any evaluator, as long as the input data is similar to what it was trained on. This model can then be used to fine-tune the AI system or influence its behavior in real time. By incorporating evaluator features in the training process, we can enhance the model's ability to generalize to different evaluators. Furthermore, we explore different ways to incorporate diverse individual input or feedback into AI systems using social choice theory methods. One approach involves adding a preference aggregation step during training, potentially transforming RLHF into RLCHF, reinforcement learning from collective human feedback. Another approach suggests introducing a simulated collective decision step either during training or in the real-time decision-making process of the system. Section Summary. In this section, we explore methods to handle diverse and informal feedback in training AI systems. By introducing individual evaluation interpretation and preference models, we can convert varied evaluator feedback into a common form for AI system steering. This process involves training models to interpret and aggregate feedback, ultimately aiming to fine-tune AI systems or guide their behavior in real time based on collective human feedback. Section. Proposal. Simulated collective decisions. In this section, we propose a new approach called simulated collective decisions. Instead of using reinforcement learning with numerical rewards, we suggest using social choice methods to make decisions collectively. This involves simulating a group decision-making process rather than simply aggregating individual preferences. To implement this approach, we can transform the existing RLCHF model into supervised learning from simulated collective decisions. In this new model, instead of combining individual ratings to get an overall score, we simulate a collective decision to choose the best response directly. This collective choice is made by a single winner social choice function. The AI system is then trained using supervised learning based on the chosen response. Alternatively, we can use a multi-winner social choice function to select multiple responses and combine them creatively, such as presenting them as a list of options. Another radical idea is to skip the training step entirely and simulate the collective decision-making process at the time of making a decision. When considering traditional social choice concepts, it's essential to focus on the most relevant ones for the specific application. For example, concepts like false name-proofness may be crucial for online voting but not relevant for in-person meetings. Therefore, we should carefully select which traditional concepts are most important for aligning AI systems. One important concept to consider is the independence of clones. Clones are alternatives that are very similar in terms of individual preferences. The presence of clones can impact the outcome of a decision-making process. For instance, in a voting scenario between two restaurants, introducing a new option that splits the votes can change the final result. Ensuring independence of clones is crucial, especially when selecting responses for a chatbot, where similar options are common. Section Summary. In this section, we propose a shift from reinforcement learning to simulated collective decisions in AI systems. By using social choice methods, we aim to generate responses based on collective preferences rather than individual ratings. Concepts like independence of clones in social choice theory become crucial in scenarios where similar alternatives can significantly impact the outcome, such as selecting responses for chatbots. Section. Strategic voting. In this section, we discuss strategic voting, which involves casting a vote that does not truly reflect our preferences in order to achieve a better outcome for ourselves. This can be a problem as it makes it challenging to trust votes or feedback. Different voting rules may create incentives for manipulation, especially when voters have information about each other's preferences or the voting rule. Strategic voting in a context like RLHF could involve overreporting ratings to influence the final outcome. For example, giving a lower rating than one's true opinion to offset higher ratings from others. This manipulation can affect the final average rating but not the median, which remains unaffected by strategic voting. Anonymity is another important aspect in voting rules, ensuring that swapping votes between two voters does not change the outcome. This principle aims to treat all voters equally and prevent any form of weighted voting. However, in AI development, there may be situations where considering the expertise or influence of evaluators could challenge anonymity. It raises the question of whether traditional democratic norms in voting apply in AI contexts. In social choice theory, we usually consider human agents as voters, but in AI ethics and safety applications, ethical principles could serve as voters to evaluate AI outputs. This approach offers a different way to apply social choice theory to AI systems, where ethical principles guide the evaluation process. This model suggests a middle ground between entirely principle-driven systems like constitutional AI and purely data-driven approaches like RLHF. When considering human preferences in AI systems, we must account for behavioral aspects and cognitive biases that may influence how preferences are expressed. While preference elicitation theory often assumes ideal conditions, real-world human behavior introduces complexities. Correcting for these effects raises questions about aligning AI systems with human values and the risk of losing valuable information through corrections or potential misuse of correction mechanisms. Section Summary. In this section, we explore strategic voting, which involves casting a vote that doesn't align with one's true preferences to achieve a desired outcome. Anonymity in voting rules ensures fairness by not favoring certain voters, while considering ethical principles as voters offers a unique approach to applying social choice theory in AI contexts. Additionally, accounting for behavioral aspects and human cognitive structures in preference elicitation raises questions about correcting for biases without losing valuable information. Section: How to navigate a multiplicity of ICE. In this section, we discuss how to handle a variety of AI systems. Consider a scenario where a group of people is voting on which restaurant to go to for dinner. If there is a big disagreement in the votes, instead of making the minority go to a restaurant they dislike, it might be better to split into smaller groups, each going to a different restaurant. Similarly, in dealing with AI systems, it could be useful to have multiple systems to account for diverse cultural differences in non-uniform populations. Feedback providers could be divided into groups based on different criteria, either beforehand or afterwards based on their feedback. This is related to the concept of representation in voting theory. Another situation could be when a group feels that an existing AI system does not serve them well, prompting them to create their own system by pooling their resources. Cooperative game theory, also known as coalitional game theory, addresses these ideas and their connection to representation. However, creating multiple AI systems may have drawbacks, such as unnecessarily dividing people or not aligning with existing social structures. For instance, a country like the US may prefer a single system to impact all citizens rather than splitting into multiple systems. Additionally, multiple AI systems may need to interact, potentially leading to conflicts between ICE with different objectives. Exploring cooperative AI literature can help manage these interactions effectively. It is important to try to avoid having multiple ICE with conflicting goals or design them in a way that minimizes potential conflicts.